We now begin to take a look at quantitative examples involving the work energy theorem. The work energy theorem states the following. When net work is done, the transferred energy results in a change in the object's kinetic energy. Kinetic energy is the energy associated with motion. It's the simplest form that energy takes. A moving object must contain energy because a moving object can do work on something else. The role of work is to transfer energy, and the mathematics of the dot product describes energy transfer perfectly. Okay, let's take a look at the first of our quantitative examples. It's an example that we have seen before. Let me read it to you here. Make sure, of course, that you write it down in your notes. Okay, calculate the distance traveled by a hockey puck on horizontal ice if the initial speed is 5 meters per second and the coefficient of kinetic friction is equal to 0.2. First, solve the problem using Newtonian mechanics. When you set up a problem involving F equals ma as your starting point, that approach is referred to as Newtonian mechanics. This is, of course, what we've already done in our previous unit on dynamics. When you set up and solve a problem, however, by using F equals ma as your starting point, it doesn't say anything at all about energy transfer. So then, therefore, after we have done that task, we'll then resolve the problem, but in that case, what we'll do is we'll use the work energy theorem as our starting point, and we'll get a much deeper understanding as to what is happening physically in terms of energy transfer. Okay, so let's go ahead and set up the problem the old way, if you will, by using, for example, Newtonian mechanics. Okay, so very simply, here's our situation. We have our hockey puck like so. It has some mass m. It has an initial speed of 5 meters per second to the right-hand side. It ends up at rest over here. And then ultimately we have here an unknown displacement vector, delta r. Okay, the coefficient of kinetic friction is given to us as 0.2. So here's, of course, how we would have solved this problem in the previous unit. We'll do a little bit of F equals ma to find the acceleration, and then we'll use a little bit of kinematics then and ultimately to find the displacement. So let's go ahead and use F equals ma as our starting point by setting up our force diagram. Now, as the object slides to the right-hand side, and here's how I would describe it. Take, for example, an object and just slide it like so across the desk, where once again the problem begins when the object leaves my hand. Okay, now, as I said, let's go ahead and set up our force diagram. So as the object slides to the right, we have, first of all, vertically, the normal force and the weight canceling each other out. Right here is the force of kinetic friction. That's then going to give us our acceleration. And then right over here off to the side, I'm going to draw the displacement vector as well. Okay, adding up the forces now horizontally, we then end up with the force of kinetic friction is equal to the net force ma. The force of kinetic friction is the coefficient multiplied by the normal force. And the normal force in this situation, of course, is equal to the object's weight. Like so. Okay, the mass of the hockey puck cancels from the expression, like so. And now we just go ahead and we calculate then the acceleration. The acceleration is equal to the coefficient multiplied by g. So very simply, I have 0.2 times 9.8, and ultimately this comes out to be 1.96 meters per second squared. Okay, the acceleration vector is to the left-hand side, so then therefore when I now set up the kinematics to solve for the displacement delta r, I have to make the acceleration vector a negative value. And the reason for that is because I'm defining, for example, here on my diagram to the right-hand side as the positive direction. Now to find the displacement vector delta r, we'll just use the third kinematics equation. Okay, here's how I'm going to write the third kinematics equation, however, in this context. Notice in the last term here that I'm writing the displacement as delta r. And now let's go ahead and plug in our final velocity as 0 and then solve for delta r. Okay, so plugging in my 0, like so, and now solving for delta r, we'll move the v naught squared to the other side. We pick up a negative sign when we do, and then divide by 2a. Like so. Once again, however, when I plug in the acceleration, I have to make this here a negative number. That negative number for the acceleration will cancel with this negative number here. Okay, so now let me go ahead and plug in the numbers, and I have first of all v naught squared, so 5 squared in the numerator, and then ultimately divided by 2 times 1.96. All of the negative signs cancel out. This ends up being about 6.38 meters, like so. So a basic problem involving Newtonian mechanics using F equals ma as your starting point, typical of what we saw in the previous unit. Once again, this says nothing at all about energy transfer. Okay, now let's go ahead and resolve the problem by using the work energy theorem as our starting point. And ultimately, here's then how you begin. We write the work energy theorem as net work equals change in kinetic energy. The right-hand side of the expression is always the same thing in the following sense. It's the final value of 1/2 mv squared minus the initial value of 1/2 mv squared. The quantity 1/2 mv squared, remember, is interpreted as the energy associated with motion. It's the object's kinetic energy. Now in this particular case, because the final speed of the object is equal to 0, the final kinetic energy is equal to 0. And then we subtract the initial kinetic energy here on the right-hand side as well, where we do have an initial speed here, v0. So we're taking the final value of 1/2 mv squared minus the initial value of 1/2 mv squared, where the initial speed here is v0. That's how you always begin the right-hand side of the expression. You deal with the change in kinetic energy first. And then on the left-hand side of the expression, that's essentially what we did earlier in this unit. That is when we were practicing calculating work for various forces. We then calculate the work done by the various forces and add it all together to get the net work done. That then goes here on the left-hand side of the expression. So now let's go ahead and calculate the work done by the individual forces, and let's interpret what the work then means in light of the work energy theorem. So first of all, let's take a look at the work done by the normal force. So the work done by the normal force is the dot product between the normal force vector and the displacement vector. So let's go up to our diagram here on the top board and then realize that there is a 90-degree angle here between the normal force and the displacement delta r. Cosine of 90 degrees and the dot product is equal to 0. Okay, now we know what this means in light of energy transfer. When the work done by a force is equal to 0, that force neither transfers energy to or removes energy from the object. This force does not add energy to or remove energy from the object. The normal force all by itself does not have the ability to do work. It does not contain energy. The only situations in which the normal force can do work is if an outside energy source is present. For example, let's say that I take my clipboard and I have my calculator like so. Right now there is a normal force vector acting upon the calculator. However, if I then do this like so, in this direction upwards, you have the normal force and the displacement. So yes, in this case, work is being done by the normal force. But in order for that to happen, I have to be present. An energy source has to be present. If an energy source is not there, for example, if I just set the clipboard on my desk like so, at no time in the future is the clipboard all of a sudden going to start pushing the calculator upwards. If that was the case, where did the energy necessary to do that come from? It would have come out of nowhere. It would have been created, which is physically impossible. Incidentally, by the way, this is the physical reason why that all superhero movies are fantasy. All superhero movies, they completely violate the work energy theorem. Where did all the energy necessary to do all of those fantastical things that you see in the various Marvel movies, for example, where did that energy come from? It came out of nowhere. So ultimately, movies such as that are pure fantasy. Okay, now getting back to our problem, let's go ahead and calculate the work done by gravity. Okay, so the work done by gravity, by mg, is equal to the dot product between the gravitational force vector and the displacement vector. So if we look at the diagram above, there's a 90-degree angle between mg and delta r. Once again, the cosine of 90 degrees is equal to 0, so then therefore no work is done by gravity. So if no work is done by gravity in this horizontal situation, gravity does not transfer energy to or remove energy from the object. Okay, and then next we take a look, of course, at kinetic friction. Okay, so the work done by kinetic friction is equal to the following dot product. It's the dot product between F sub k and delta r, and we have seen in previous problems earlier in this unit how we go about making this calculation. Okay, let me give myself some room here. Let's do some erasing. Okay, and now the work done by kinetic friction is equal to, first of all, the magnitude of the first vector, recall how to calculate the dot product, times the magnitude of the second vector, and then multiplied by the cosine of the angle between the two vectors. As we've already seen in our practice calculations, there is always a 180-degree angle between F sub k and delta r. Remember, of course, that the force of kinetic friction always opposes the motion, so then therefore you end up with the cosine of 180 here in your work calculation, which is equal to -1. Like so. Okay, and now the force of kinetic friction, this is of course equal to the coefficient multiplied by the normal force, and the normal force is equal to the object's weight. Like so. So we have this quantity here now for the work done by kinetic friction. It's a negative number. So what does the negative sign mean? What that means is that this force, kinetic friction, removes energy from the object. So if kinetic friction is removing energy from the object, where is that energy going? Well, it's actually becoming another form of kinetic energy. For example, let's say that I take my eraser and I slide it across the desk like so. As the eraser slides across the desk, due to kinetic friction, it slows down. So what happened to the initial kinetic energy of the eraser after I let go of it? Well, it's becoming another form of kinetic energy. As the eraser slides across the desk, the eraser does work. It does work on the atoms that make up the surface of the desk, causing them to vibrate in place with a little bit more kinetic energy than they had prior to the eraser sliding across the desk. In other words, what we have done is we have transferred heat to the desk itself. The word heat refers to another form of kinetic energy. It's the kinetic energy associated with the molecules of a substance. If we had a sensitive enough thermometer, we would then measure a slight temperature difference for the desk from the eraser prior to sliding across the desk to after it slides across the desk. We would find that the temperature of the desk is a little greater after the eraser slid across the desk because the kinetic energy of the eraser became another form of kinetic energy, and that's heat, the kinetic energy associated with the molecules of a substance. Now, of course, you study heat, for example, in, say, chemistry class, when you look at various types of chemical reactions, whether they be endothermic or exothermic. Do you recall what the metric SI unit for heat is from that class? It is 1 calorie. 1 calorie is equal to the mechanical equivalent of 4.2 joules. 1 calorie, by the way, with a lowercase c, is the amount of energy necessary to take 1 gram of water and raise its temperature by 1 degree Celsius. So if this number here, for example, was equal to negative 4.2 joules, just for the sake of argument, what that would then mean is that we have transferred 1 calorie of energy of heat to the desk. Notice that ultimately, F equals ma, Newtonian mechanics says nothing at all about this. Okay, so now what we do to finish our problem here is we take this guy here, the work done by kinetic friction, and that then goes here into the left-hand side of the work energy theorem. Recall that the work done by the normal force and by gravity are equal to 0, so then therefore the left-hand side of the expression is one thing, it's the work done by kinetic friction. Okay, let's go ahead and write that out. Like so. Okay, and now mathematically, let's just go ahead and get rid of this 0 here like this. And at this point, let's go ahead and cancel the negative sign, like so. And when we do, we arrive at this expression here. This expression here is the most important part of this problem. The reason why is because this expression is a perfect description of the energy transfer. Always think of the energy transfer as what form of energy becomes what other forms of energy. In this particular case, the energy transfer essentially happens in this direction, if you will, in the expression. This right here is the initial kinetic energy of the hockey puck or of the eraser as it slides across the desk. And then what happens to that initial kinetic energy? It becomes this. This right here is the heat that is transferred to the surface below. So the object's initial kinetic energy transferred to the surface below. Once again, Newtonian mechanics says nothing at all about the energy transfer. Okay, now mathematically, let's just go ahead and finish the problem. At this point, recall that what we're solving for is the displacement delta R. So let's go ahead and cancel out the mass, like so, and then move the coefficient times g down to the denominator here on the right-hand side of the expression, thereby solving for delta R. And then let's take a look at the expression that we have left over once we do this. Like so. And now, before I plug in the numbers, take a look at this equation here, which we just derived by using the work energy theorem, and from earlier, using F equals ma, this equation here. Is this equation here the same thing as this? Yes, and the reason for that is because recall earlier that the acceleration is equal to the coefficient times g, and that went into the denominator of the expression. So of course, if we plug in the numbers into this expression, we would get exactly the same thing as we did before when we solved the problem by using F equals ma as our starting point. Of course, here in this case, the displacement is once again 6.38 meters. Now there is a slight difference in the expressions, that is here, and that's of course this negative sign. The reason for that is as follows. Recall that everything up that we did up here on the top board involves vectors. F equals ma, of course, is a vector expression, and kinematics involves positive signs and negative signs for the vectors that describe motion. So everything that we did here on the board is in terms of vectors. This guy here, however, is a scalar. The reason for that is because recall in the dot product that you end up with magnitudes. You end up with the magnitude of the individual vectors. So because the displacement delta R here is a magnitude, it's the distance traveled in this problem, this then means that you're going to end up with a positive number. So when you solve for one of the terms here, such as delta R by using the work energy theorem, you're going to get a positive value because ultimately what you're solving for here is a magnitude. So this right here is a magnitude for the displacement, whereas everything that we did up on the top board involved vectors. Ultimately, however, we do, of course, end up with the same expression here as we did here. This means that technically you could actually set up and solve a problem by using either method. You could set up and solve a problem by using, for example, F equals ma as your starting point, as we did here on the top board, or here on the bottom board by using the work energy theorem, and of course, ultimately you get the same answer. A little bit later on in this unit, we're actually going to see a specific force that you're going to be taught backwards. You're going to be taught how to deal with that force by using the work energy theorem first, because it's mathematically a little bit easier to do. And then a little bit later on in the course, then you'll learn how to treat that force by using F equals ma. But I'm getting a little bit ahead of myself here at this point. Let me go ahead and conclude this portion of the lecture here.